Right. Okay. Welcome everyone to the third session. Today we'll talk a bit about how we can sort of measure performance in our code, and we'll begin talking about optimization as well. We'll do some today and some on Thursday as well. So the aims for today are to be able to actually profile and benchmark our code, to be able to understand something called computational complexity, and again, to cover some sort of basic optimization techniques. So on the first hand, when we're measuring performance, we want to sort of quantify the resources that are used. So what sort of resources are interesting in our case when we want to optimize? Any examples?
Memory.
Yeah, so memory is an example. We have a finite amount of it and we want to make sure that we're making best use of it as well. Something else? Time, exactly. So memory and time are the two most important things that we want to think about, but we can sort of break these down into different sections, but those are the main two that we want to focus on. So yeah, so the first is like time. Usually we refer to wall time. So if you start executing a piece of code, you click a timer at the start and you click a timer at the end and measure the difference. That's the sort of wall time, how long it actually takes to execute. Another resource is the CPU. So what should be sort of proportional to the wall time is the number of clock cycles. So a CPU can do a certain amount of instructions on every cycle. And those are they're usually measured in whole units. But also CPUs have multiple cores. So how many cores are you using? And we started to talk about cache as well. So how effectively are you using the cache? Again, there's memory, as we said before. And this has two parts to it, just how much memory are you actually using, and also the bandwidth. So how many like gigabytes per second are you reading and writing from memory, which is also limited as well. If you have a lot of data, you also have storage as well. And again, just like memory, this has a sort of limited I/O, so how fast you can read and write to your storage. And finally, this might not come up a lot, but network sort of input and output tends to be quite slow as well. So that is something that can sort of bottleneck your code. Today, we're just going to focus on sort of timing and memory usage. So the way you can basically measure wall time is using the CPU's internal clock. So it needs this clock to be able to sort of synchronize its behavior, and you can sort of make use of that to time your code. So in Julia, you can use the @time macro, but it's not very accurate. So we have to use sort of alternative methods to get a better idea of how long our code is actually taking to execute. So we'll give an example here. So let's just define a function that takes some sort of input array, and what it will do is it will cube each element and add it all together. This is just a sort of shorthand notation, but the sum function can take in, this is called a lambda, like an anonymous function, that will make it so you don't have to allocate another array for the cube and then sum that on its own. So the way we call this is you just create an array here. It's just random floating point numbers, and you can use the @time macro on the front, which will execute the code, and it will tell you how long it takes, and it will give you some other information about it as well. So what's important in Julia is the first time you call a function, it has to be compiled. So you can see here, this took about a 20th of a second, but it says that 99.96% of that time was just compiling the function. But so if you run it again, you'll see that this takes far less time, and it won't give you a sort of big breakdown of the compilation time because it's already been compiled. So you only pay this compilation cost once at the start, and if you call it multiple times later, it will use that cached compiled version of the function. So yeah, if you're using the @time macro, you always have to measure twice to get an accurate reading of how long the code actually takes to run. Instead, you can use benchmarking. So we saw this a little bit last week, but there's a package called benchmark tools, which gives you some other macros other than just at time that will execute your code multiple times and give you the sort of distribution of times that it takes. And this can be a lot more accurate as well. So first thing that you might notice that's a bit strange is there's this dollar symbol on the front of the variable name. This is for interpolation. So essentially global variables tend to be less performant when you're using the REPL. And this is a way of just sort of abstracting away that cost and making sure the benchmark is accurate. Don't need to go into too much detail on this, but when you're passing in variables, just put this little dollar sign on the front when you're using the benchmark macros specifically. These results are far more accurate than using at time. At time can be quite misleading. So if you're ever actually benchmarking something, either use this macro at benchmark, or there is another one called at btime, which acts just like time, but it will take multiple repeats of your code. Yes. So the importance of this is obviously you'll get a distribution of times because even if the code is doing the exact same thing, it will take different amounts of time to execute depending on what else the computer is doing and a few other factors. So as you can see from the benchmark, the time taken to execute can actually vary quite a lot. And some of this variability is to do with scheduling. So let's say your computer only has one CPU core and you're running the program on an operating system. The operating system needs time to run. Also, you might have other programs open at the same time. And the way you can have those programs running together, so concurrently, is you give a small piece of time to one of your programs, let it execute for a while, and then you stop executing that and switch to another task. And this is done by interrupting the process. So basically, whenever you're benchmarking, you kind of have to make sure that you're not running a lot of other tasks as well. And you also should take repeats to sort of factor out this interrupting and scheduling behavior. Also, something that's more important when we come to parallel programming is basically how hot your computer is may determine your clock speed as well. So if your computer is getting too hot, then it may lower the clock speed to reduce the amount of heat, basically just to protect the components. So you may have noticed this on a lot of modern computers. They'll advertise a boost clock. So if you're using like a single core, the CPU will run that core a lot faster than the rest of the cores to give improved performance on sort of your single-threaded code. But then if you go to use multiple cores, then it won't be able to dissipate the heat from running all of them at the same speed. So it has to lower the speed to make sure it doesn't overheat. That will make sense. So benchmarking is one way you can look at a single sort of function in your code and sort of determine how fast or slow it is. But if you go into a big code base where you don't actually know which functions are the slow ones and there's a lot of things to check, an alternative approach is called profiling. So the main approach that we use in Julia is called statistical profiling. And what this does, it will run alongside the code you're executing and just check sort of in which functions is the code at a certain time. And so whenever you're executing your program, it will have your stack frame of which functions you're currently in, and it will take note of where you are at each sample. And this sort of sample can be used to sort of extrapolate how long is spent in each function. Because if you end up in a function 10 times as often as another function, you know that function approximately takes 10 times longer. These results are usually shown as a flame graph. And this is sort of common throughout most languages. We use a flame graph to show how long each function takes. So this is one example from Julia. It can be quite hard to read, but if we're sort of wanting to talk about optimization, you want to focus on the functions that take the longest amount of time. So the width of these bars will sort of indicate how long that part of the function took. And you can see there's a sort of hierarchy of top to bottom. So usually you'll have one function that calls multiple other functions. And if a function calls a function, then it gets put below on this flame graph. So let's see if I can draw on here. So you can see there's this function called solve here, and it contains a few function calls. Inside it calls a method called prune, also backtrack, and this constrain solver as well. So the solve function takes a long time because it's spending a lot of time inside, or spending a portion of its time inside this prune function that it calls, but it's spending the majority of the time inside this backtrack function. And these graphs usually come up as an interactive mode, so you can click on the different functions and sort of drill down into what's actually taking the most time. So this is a sort of overarching way you can really quickly identify which functions are taking the most time in your program, because they'll be the largest on this graph. We'll have a look at an example of using this later for memory profiling, but this one's for time. Okay, so the sort of technique to put them all together is you use this sort of profiling. If you have a big code base and you don't know which functions are actually slow, you can identify which ones are slow, and then you sort of drill down and use the benchmarking tools to make sure that you can sort of understand the performance of the slow functions. And the reason we do this is because optimization takes a lot of your time, and often the code that comes out will be sort of less readable, less easy to maintain than before. So you basically only want to actually optimize the parts that will make a big difference to your program. If a function only takes 1/100th of the time, the total execution time, there's no point optimizing that. You should focus on the rest of the 99%. I would always recommend keeping your old code so you can compare the difference between them. So you can have sort of 2 copies of a function with a slightly different name. This is for a few reasons: to make sure that what you're actually doing is improving the performance, and to make sure that it's still getting the correct results as well, because you can run the results through and basically check that they're the same. One important thing here is this is all very hardware dependent. If you move to another computer, you'll get completely different results. So stick to the same machine when you're comparing the difference between your programs. And again, sort of minimize the number of other things the computer is doing at the same time to make sure that your benchmarks are as accurate as possible. Okay. So that's one sort of practical approach to actually timing these things, but there's a lot of theoretical tools we can use to actually measure how many resources a certain algorithm will take. That abstracts away some of the hardware details. So who here has actually seen big O notation before? Yeah, it's sort of commonly used in physics as well to get sort of order of magnitude sort of estimates. So yeah, computers are different. So this computational complexity sort of lets you measure how certain resources scale with the size of your inputs. So if you're performing a sum, for example, and you have n elements, then you know that it will, if you double the amount of elements, it will take twice as long. And yeah, so this complexity, basically, it's just a classification of how many resources are required to run a certain algorithm. And we focus mostly on computational time, but you can also do the same analysis in terms of memory as well. So if we take this very simple example, so a function on the left basically just allocates an array and loops through each element, just adding together element-wise 2 arrays A and B and storing them in the third array C. And if we plot the time taken as you scale the size of the arrays, which we'll just call n here, you can see that if you plot it on a log-log graph, you'll get a linear curve. So you could plot it normally and see that it's linear, but sometimes you'll have polynomial time, and log-log is usually the best for polynomial. So the way we fit to this line is, you see, we've got this top equation. That's just the equation of a straight line, but you've replaced the variables with logs. And if you sort of rearrange and solve this, you can see that it's just a polynomial of order n, where m is just the sort of gradient of this line in log. So you can do some maths to work out what the gradient of the line is, but in this case, it's just 1. So we know that it's linearly proportional, or the time taken is linearly proportional to the input size. So this is some equation that tells you the time to execute. And these constants, so C and T0, depend on the computer you're using and the hardware. And we know that if we move to other hardware, it's very likely to have this exact same scaling. The only thing that will change is the constants. So they're sort of less important when we're thinking about complexity. So again, you can kind of convert those constants into just any numbers, and we can sort of throw away the constant information and only keep the actual scaling laws instead. So I'll show that again. So we have these A and B, but all we care about is that it's sort of proportional to n. So this, when n gets very large, we'll drop off the constant b because its contribution is far outweighed by the contribution from n. And again, this a on the front changes, so we also get rid of that as well. So this O of n just means it's some quantity of order n at the scaling law. So there's a few ways we can do this, but the ones we usually care about is the asymptotic performance. So as you make n really, really large, sort of what does the scaling law look like? And so essentially, whenever you're doing this, you only keep the factors that grow the largest. So for example, if you have n squared plus n, you know that n squared grows a lot faster than n, so you get rid of the n, and you would only have order n squared. Yeah, this usually deals with the worst case. So a lot of times, how much computation an algorithm does may depend on the specific values of the input. But we usually analyze it so that it's the worst case scenario and take that. So that will give you a sort of ceiling approximation. Sometimes the average case is interesting as well, because you'll get a distribution of times, and depending on the shape of that distribution, you might care more about the average than the worst case. Yeah, so the main thing is this is only really useful for when you're trying to scale up an algorithm. If you're dealing with arrays of like vectors and you know that it's only going to be 2 dimensions or 3 dimensions, in that case, n is going to be very small, the number of dimensions you have. So most of the time, just stick to benchmarking, because this sort of theoretical approach won't make much difference, because the thing that matters most when n is really small are the actual constants themselves, and you get the constants from benchmarking. The way this can be used is if you know your inputs are going to be large, you can actually compare 2 different algorithms together and see whether it's useful to switch to an algorithm with a lower complexity, because you'll know that will give you more performance boost for the large sizes that you want to deal with. So we'll go through an example. So this is like the nearest neighbor problem. So you have a point cloud of different particles. And essentially what you want to do is for each of the particles, you want to find out which other particle is closest to it. So this comes up a lot in machine learning, physics. It's a very common algorithm. And it's also the one that's in the assignment as well. So it's good to get used to it now. So essentially, we want some algorithm where we put in a list of sort of particles, I call them nodes here, with some sort of random positions, and we want to output a list that gives you for each of the particles which is the nearest neighbor, which is this table on the right-hand side. So this is an algorithm that you can use to do this. This is the your simplest algorithm. For each particle, you calculate the distance to every other particle and you just choose the minimum one. It's the most sort of straightforward approach. So the way that we will calculate the complexity is you can take it step by step. So this very first line just gets the size of the input array. So it gets the number of particles and the dimensionality of the particle. So is it in 2D, is it in 3D? This takes a constant time, and the way we represent constants in the big O notation is just O of 1. Now, our next step is we allocate an array that can store n integers in it, because we want to be able to allocate an array to store this sort of output table. And my sort of assumption here is that that takes approximately linear time. So if you need to find space for a bigger array, it might take longer than for a smaller array. This is not general in any case. It really depends on the setup of the hardware and what the language actually implements. Because a lot of languages have very different rules for if you're allocating small objects to whether you're allocating big objects. So this is just an assumption, but it's going to be linear or less than linear. Okay, so now we go into the for loop. And instead of sort of carrying on with our big O notation here, what we'll do is we'll just calculate the complexity of the inner loop and then sort of propagate that information out. So the first two lines here, what you're doing is you're extracting the coordinates of one point I, and you're sort of setting a variable. And this will, again, just take O of 1 time, just a constant amount of time. It doesn't depend on your input size at all. We get another for loop, so we'll do the same sort of trick. And just to save a bit of time, every instruction here will execute in some constant time. So that won't depend on number of inputs at all. But the way we have to sort of propagate this information back is we're doing something that takes constant time, but we're doing it n number of times. So we know that that for loop will take O of n time. So we sort of propagate that information back out to get O of n. And again, now that we've come to the end of the first for loop, we can combine the O of 1 and the O of n, which just leaves you O of n. Because again, we care about when n is very large, so you can throw away the sort of constant contribution. So this whole thing just becomes O of n. And again, we finish the for loop, and we're doing an operation that takes O of n times, and we're doing it n number of times. So this entire for loop can be summarized as O of n squared. And now we have two parts to our code. We have the first part that takes O of n, and the second part that takes O of n squared. But because n squared grows faster than n, you can just focus on the contribution of the O of n squared part. So altogether, this becomes O of n squared. So ask a question. So if you have 1,000 points and you've timed your algorithm and it takes 10 seconds, if you double the number of points to 2,000, how long would you expect it to take? Is it 100 seconds? If you double the number of points.
Well, I think 100. Are you taking that? 40.
Yeah, yeah. So you increase the number of points there. So this n goes to 2n. The 2n gets squared, and you take the 4 out on the front, so it's 4 times as long. If it went to 100, that might be exponential complexity instead, I think. But yeah, so for this one, if you double the number of points, you expect the time taken to quadruple. Does that make sense? Great. Okay, so we'll give a few examples to you. You might need some time to sort of work this out, but can anyone guess what the complexity of this function is? And I'll explain a bit what it does. So you take in some number a, it's just some number, and n is like the number of times you'll do some loop. If n is equal to 1, you just return this result squared. Otherwise, you go into a for loop and you recursively call the same function, but you lower the value of n by 1. And you do this for loop n times as well. So I'll give you like a minute just to sort of think about that, and then we'll see if someone can talk me through it. If anyone thinks they have it, you can shout it out now, or a guess at least.
N factorial.
Yeah, exactly. It's n factorial. The reason it's n factorial is because you go into the for loop straight away. Most of the operations there are constant, but this for loop that we have in the middle happens n number of times. And the operation within that for loop depends on this sort of the complexity of the recursive function. So you know that you have sort of some complexity here, and it's n times the complexity of your function, which I'll just call f. So this f of n is n multiplied by the complexity of n minus 1. And you can sort of recursively substitute this into yourself. So you'll get n times n minus 1 times n minus 2, dot, dot, dot. And you know that it ends when n equals 1 because it's just constant time. So at the top, if n equals 1, you just return a value. So altogether, you'll end up just getting n factorial. Great. Next one might be, you don't see this very often. I should point that out as well. You don't see it very often. So this other algorithm is a sorted insert. So you have, let's say, a list of numbers like 1, 3, 7, 10, 12, and you want to, let's say, insert the number 9 into this array. If you know the array is already sorted, you can sort of search where to insert it more efficiently. So you start by looking at the ends of the array, and you can see that it does lie in that region, which is good. And then you take the sort of midpoint, which is this 7 value, and you say, is 9 bigger than 7? Yes, so you can look in this region here, and then you sort of iteratively keep doing that process. So you have 2 ends, you look in the middle, and you can halve the search space every time until you find 2 elements which are next to each other, and then you'll be able to quite simply insert the value into that location. So this is just some sort of straightforward code to do this. Anyone have a guess at what the complexity is?
Square root of n.
Close, not quite.
And all good.
This is very close. And not n log n, but log n, yeah. So basically what happens here is you sort of halve your search space every single time, and the number of steps it takes to complete the algorithm is directly proportional to the number of times you actually have to halve your input. So you begin with some large range here until you get a range which is just one value or less. And basically the sort of number of steps you have to take is proportional to how deep you have to go here. And so you'll have the size, which is like a half to the power of, let's say, k for the number of steps you have to go down, times n is equal to 1, because you want that width to be just one value. And yeah, if you sort of rearrange this by 1 over n, k to the power of half, you can end up getting, oh, sorry, I don't have anything. You get log 1n, and then we do a minus at both sides, so we can just get log n and log 2, k log n. So this k value, sorry, this is going to be very small. This k value is basically proportional to log n. And so it doesn't matter what log base you take. Usually when you're expressing these, you just use the natural log. But it would be easier to use base 2. So yeah, it's O of log n. And if you were to insert sort of n numbers into this, then you'd get that n log n on the front, which was said earlier. So yeah, basically the idea is if you can work out the complexity of the innermost part of your code, you can kind of propagate that value back out until you have the full complexity of a whole algorithm. Yeah, so those are just 2 examples, or 3 examples in total. But this sort of complexity lets you evaluate and choose the best algorithm for the job. So, for example, in your assignment, the algorithm that's given there is an n-squared algorithm, but there are other algorithms for doing a sort of nearest neighbor search that can do it in n log n. And n log n is much better than n squared because obviously log of n grows much slower than n grows. But those algorithms are usually much more complicated. And oftentimes the trade-off is they have sort of these really big constant factors. So you have to do a lot of overhead to actually implement these algorithms. So for smaller values, they can actually be slower. So the main thing to notice is even though the complexity of one algorithm may be better than another, if your input sizes are small enough, then if the input sizes are small enough, you really have to benchmark to compare the 2 and choose which one is best for your case. And a lot of the time, the simplicity is sometimes even sometimes better as well and preferred. Okay, great. So now we've sort of got most of the theory out of the way, we can actually start talking about optimization. So there are a few reasons to optimize our code. Obviously, the first most sort of basic one is you get your results faster. So if you're running sort of experiments with your simulations, if you can get the results much quicker, you can sort of iterate on your ideas much faster, which leads to a lot of productivity. If you have to spend an hour waiting for your code to run before you can sort of progress with any of your ideas and see whether your ideas are actually correct, that can really badly impact your actual productivity as opposed to getting the results within a few seconds. But the main reason why people are actually interested in this is because it lets you actually scale up your experiments and your simulations to much larger sizes. And these much larger sizes are often sort of more interesting and also gives you a bit of a competitive edge in the sort of scientific domain, because if you can go to bigger system sizes, then your paper looks more impressive to the journals. Also, one big one is you can use fewer compute resources. So if your code is sort of 1,000 times slower than it could be, then you're ending up using 1,000 times more resources, more money, more sort of energy, everything. So often, if your code is running for weeks and weeks at a time, it's really worth spending a few days just trying to optimize the code so it will run in like a day or 2 days. Another point is if you're sort of writing your algorithms and you project using this sort of complexity analysis and some benchmarking, you can project that if I was to double my system size, it would take a year to run instead of a week. A lot of the time, you don't have a choice, right? You have to be able to optimize the code to actually get any results because your algorithms will just scale so poorly that you need to make sure that it's as fast as possible. So this will sort of go over a bit of a misconception. People talk about code being fast and code being slow, and especially when you're comparing different languages together, like people say Python is slow, C is fast. What you really need to think about is like what's slowing the code down, because in the end, regardless of what language you're running, the instructions will get compiled down and run on the hardware. And the language shouldn't have too much influence over how fast an algorithm can run on a given machine. So usually the question to ask is, why is this slow, not why is this fast? So the main reason is you've just chosen the wrong algorithm. So if you're, for example, if you're doing a nearest neighbor search, when you're like implementing a sort of galaxy simulation to try and work out all the gravitational interactions. In a galaxy, you'll have billions of stars, and so your n is going to be very, very large. So if you've chosen an n squared algorithm over an n log n algorithm, then you're just going to have no chance. That's probably the main reason why it's going to be slow. Another main problem is your code can be doing things that it doesn't actually need to achieve the result. So if you're calculating, so a lot of the time people will put in some code that they use for debugging, like calculating these intermediate values to make sure everything's working right. And then they'll keep those calculations in even when they don't need them. So when you're running your code in production. So yeah, keep a check for like unnecessary operations. But the sort of main reason why you get differences between languages is the computer or the program has to spend time working out what it's actually meant to be doing, as opposed to just executing what instructions you want it to. So this comes back to the idea of types. So in Python, the types of values can change over time. And so when you're executing your for loops, it has to check what type the number is. Oh, it's an integer, and I'm adding it to another integer. Therefore, I use sort of this CPU operation. And that operation you choose depends on the types of the inputs, because that represents differently in memory, and all of the reasons we spoke about in the first one. So doing this sort of working out what to do can take up a lot of time as opposed to just executing the code that you want. Yes, so another reason, sorry to call out Python again, but a lot of the time you have to write your code to sort of cooperate with the sort of design principles in the language. So people have heard before, if you're using Python and you want your code to run quickly, instead of using for loops, you should vectorize your code by using NumPy. But the way that you sort of vectorize has some limitations because you're still in Python and you have to sort of communicate with NumPy. We'll go into a much more in-depth example on that. Yeah, so we'll talk about that last point a bit later. So one thing to consider, this diagram might be a bit difficult to read, but it's in the lecture notes if you want a closer look, is different operations in the CPU take different amounts of time. So doing really simple operations like adding two numbers together once they're already in the CPU register, the registers in the CPU, takes like less than one clock cycle. Like it's very quick. Even writing to memory is quite quick as well because you just sort of send the value off and forget about it. By the time it might take a while to actually get into memory, but you can sort of send it out in one operation. One thing that I do want to sort of point to is there's these sort of branching. So the fourth one down says the right branch of an if statement. So if you have an if statement, the CPU will try to predict which branch of the if statement to execute. And because checking the sort of Boolean condition can be quite slow, it'll just start executing one of them. It'll pick one of them to do. And if it chooses correctly, then there's not much cost associated with that at all. But if it chooses incorrectly, it will take like an order of magnitude longer to sort of undo all of those calculations and start doing the correct calculations from it. So you don't have a lot of control over sort of branch prediction, but it's one of the main reasons people try and avoid if loops in their sort of performance critical parts of their code, because they can lead to really poor performance if it's hard for the CPU to predict which one will be used over another. Some of the other key points on this diagram are the reads from the cache. So yeah, you can see this. So we have this sort of L1 read here, which can take order of like 4 CPU cycles, more than just like adding numbers together. And these sort of the penalty for like going further away from the CPU is seen here. So from going from L1 to L2, you go from 3 to 4 clock cycles to about 10 to 12. And then to go from the L2 to L3, you go from around 10 to 12 clock cycles to around 30 to 70. So it's much, much slower the further away you get from the registers on the CPU to actually fetch memory. And then you see the sort of main RAM read is like in the 100 to 200 clock cycles. If you want to have a close look at this, again, they're in the lecture notes, but the key things to pick up from here is getting data from cache or from memory is quite slow compared to actually doing operations on your CPU. And also, if loops tend to be quite a big performance hit. And oftentimes you can write your code in a branchless way to do effectively the same thing as branching, but it sort of avoids that part of your code. So for example, if you want your function to have, if you want your function to be one of two values based on some Boolean condition, so I write it on the board so everyone can see. So if you say, so if you say you have some variable x and you want to say if some condition y, sort of x is equal to 5, otherwise x is equal to 2. You can rewrite this in a branchless way by just saying x is equal to 5y plus 2 times 1 minus y. Hopefully that's clear, because y, if it's a Boolean value, will be evaluated to 0 or 1. So if y is true, then you'll do 5 times 1 plus 2 times 1 minus y. So only one term in this addition will actually be correct, will actually be non-zero, I should say. So you'll see this quite a lot in code to try and sort of minimize the amount of branching in your code. Okay. Make sense? So we sort of spoke about this a little bit last time when someone asked about the sort of vectorization form. So just to give an example here, on the left, you have some native Python code. So you write your for loops like normal, you append values into your array, and use the sort of inbuilt math library to calculate everything. Whereas in NumPy, you can essentially calculate all of the values in the array at the same time by using these vector instructions instead. The NumPy version is obviously a lot quicker than the Python version. That's why people tell you to do it. And also the code is a bit simpler as well. You don't have to be writing these for loops. You can write it in this vectorized format. And by here, vectorized just means you're doing operations like element-wise on an array, and you're doing them all at the same time. So if we compare this to Julia, there's two implementations on the left. The one at the top is basically the same as a NumPy syntax. And so you take this input array x, and then if you sort of calculate the exponential times the sign, the expression, the only thing that's different, which you should pay attention to, is there's this little @dot macro on the front. This @dot macro is the sort of broadcasting notation. And so usually when you want to sort of calculate something element-wise, you use the dot notation to broadcast it. And again, so if you're going to do, you want to work out the sign element-wise of x, so the equivalent of np.sign of x, you just call the sign function as normal. Doesn't have to be in a special library. And then you'll put a dot after the function name, and then pass in the array here. And this @dot macro just puts in all the dots for you, so you don't have to do it yourself. So if you have a really long expression, you don't have to put these dots everywhere. This notation will come up a lot throughout the rest of the course, so you'll have time to become comfortable with it. But your sort of other approach is to just write the for loop. So here is exactly the same code, just written as a sort of normal for loop, no sort of notation to do broadcasting. And as you can see, it's basically the same speed. So both of these functions take about 900 microseconds to to actually compute. And if you compare this to NumPy, it's mostly the same. It's about 3.5 times faster than the NumPy version. And the main reason here is because when you're calculating this big long expression, each term you have to allocate a new array and then come back. So here what you're doing is you're doing the exponential of x. So you allocate a new array to store the exponential of x, and then you allocate an array to calculate the sine of x, and then you allocate another array to times them together, so on and so forth. So the version in NumPy is doing more than it actually needs to. What happens without the dots? It will give you an error. If a function is only defined for, so you define a function just for a single input, let's say you restrict it to only take integers, and you try and put an array into it, it'll give you an error saying there's no method that takes an array of numbers inside. I think for a lot of the sort of base library functions, if you pass it an array, it will allocate a new array, just like NumPy does for a lot of the base functions. I'll try that out at some point, but usually the dot notation is the way to go. And it's being explicit about what operations you want to do element-wise and what operations you want to do on the entire array. So an example is you can calculate the exponential of a matrix, and that will give you a different result to if you element-wise want to calculate e to the x for each element in a matrix. So there's a reason for separating the two, because they mean different things. What, the empty macro? Maybe you can't see it, but there's a dot here at the front. So it's an at, like period, like just a dot. Other than that, I'm not sure what the empty one means. Yeah, this at dot. So the at dot will rewrite your expression. So for example, you can write your expression like normal. So imagine that's a correct at sign. So if you do at dot on the front, it will basically put a dot in front of all of your functions and operators. So sine dot of x. So without this, you'll just have y equals sine of x. And if you put the at dot on the front, it will just rewrite your expression to put the dots in all the right places to make sure it's element-wise. To be honest, I don't really use that notation a lot myself, because usually I just have one function and I just write the dot in to be explicit. But this may come up if you're reading someone else's code. All it does is rewrite the code to put dots in, that's all. Yeah, so it's broadcasting. Yeah, that's right. Okay. Yeah.
So if I was to use that expression without the at dot, but just put the dots in the individual parts, would it not allocate memory to say calculate exponentials of all the x's because that's the order it appears? Or?
Yeah, so I think that's yeah. So the main difference between this is when you use your broadcast notation, Julia will fuse the operations together. So essentially write the same for loop as we showed before. So instead of allocating these intermediate results, it will sort of write a function that will do each thing element-wise and then just apply that function as a whole. So yeah, the main reason to use broadcasting is this fusing. And that's the main difference between Julia and NumPy here, is you can fuse operations in Julia, but because Python, you have to communicate with C. The C library doesn't actually know which ones need to get fused. There are packages like number, which will be able to sort of compile the Python code so that it will be able to fuse the operations. So that's one reason why number can be so much faster than normal Python. But the main sort of difference here is whether you write your code in a vectorized format or whether you're writing it as a for loop. It's pretty much just an aesthetic difference between them. If you're doing it in NumPy, the for loop is just in C. Like it's just moved to a different place, but you're still doing your for loop. One thing that, again, we touched on last time is we looked at this at SIMD macro. If you're doing a really typical operation, the compiler will sort of use these vector instructions for you anyway. So you don't actually have to put in this at SIMD macro, usually ever. And again, everything is native Julia, you're not passing it to any other language. So whatever native code you write there will be just as fast as if you were like using like a NumPy function to do something.
Jamie, but what you said, Loop, is this difference in compilation time is explained because of what you said, right? It's not a random thing. Because
Compilation time
has some more assignments.
Can you say that again?
Isn't it what you said to Luke? Luke asked, what's the difference between the first and the second example, the broadcasting and the vectorization, right?
Well,
if you have more assignments with the broadcasting.
I meant more using the macro or just putting the dots in every place.
Oh, right, yeah. The macro and putting the dots is exactly the same. There's no difference between them.
Yeah, but the difference between the vectorization, the second example, and the broadcasting, is it just a random thing, or is it because you have more allocation in the broadcasting?
As in the difference in the time between them. So I was trying to think about this before. I think the sort of main difference is when you do all of these broadcasting operations, Julia will check whether all the sizes work out for you. And in the second example, we're saying everything's in bounds, do no size checking comparisons at all. That probably won't make up the big difference between them. But also something that happens on the CPU is there are a lot of heuristics as to how to compile code to sort of speed things up. And it just so happens in this case, writing the inner for loop was easier for the heuristics to write some very efficient code that ends up being a bit faster. That's my theory for the difference between them. Okay, so yeah, just to touch on this point as well, this term vectorization is used throughout computer science, and in typical computer science fashion, they give different meanings to it based on the context. And it just so happens in this case, the context is overlapping, so it makes it a bit confusing. So when I'm talking about like vectorization, I'm talking about using this broadcast dot notation. So the way you're used to it in NumPy. Again, this is just the sort of aesthetic reasons for it. But there is also the hardware sort of SIMD, or hardware vectorization, which is physically doing the operations at the same time for multiple values. And again, this at SIMD macro that we introduced last time essentially just gives the compiler more leeway to introduce these operations. So there we were doing a map, so one input, one output, but last time we were summing things up and we're doing a reduction. And as we saw, doing a reduction actually changes the values that you get out of it because floating point math is not associative. So the compiler will do it automatically when it's sort of safe to and when it's easy to infer. But this at SIMD macro will sort of give it more leeway to be able to reorder your operations and sort of change which ones are considered safe. Everything in Julia as well, if you're in the REPL, if you type the question mark, you can search documentation for help. So if you type the question mark and type at SIMD, it'll explain all of this. So if there's any macros you don't understand or any functions you don't understand, just question mark, type the name, and it will give you the information. Okay. Don't have too much time yet left, so I'll just try and get through this quite quickly. So arrays, the way they're stored in memory is just as one contiguous block. So that just means every array or every element of the array is right next to each other. It's not separated out into smaller blocks across memory. And this basically means if you do operations on your array sort of in a predictable order, so from the smallest element to the largest element, then the CPU can predict which elements you'll need in cache. So what happens is, let's say you're looking at the start of the array, the CPU will say, I don't have any of these elements in the cache. So it'll go out to memory, and instead of just fetching that one value, it will fetch an entire line of memory and store that in the cache. And if you were to iterate to the next element, it's already in the cache for you. So it'd be a lot quicker to access the next element. And these cache lines will come up next week as well, when we talk about some issues with parallelizing your code. So the question is then, if all arrays are just this one big sort of serial block of memory or linear block of memory, how do you store the multi-dimensional arrays? And this is a sort of choice you make when you're implementing it yourself. So if you were to store a 2D array, there's two ways you can map a two-dimensional array onto a one-dimensional space or a linear space. So I think row major is what NumPy uses. So basically this means, if I change the highlighter, the first element in both cases are stored in the same place, but row major means that the next element means the one in the column to the right. And then when you get to the end, it goes to the next row. So you can kind of think of getting this line and sort of stretching it out. And that's how your memory is stored, is just in one big long array. Julia uses column major. So instead of going across the rows, it goes down the columns, and so it goes column by column instead of row by row. And basically the only difference between these is how you take some indices like I and j. So if you have, in this case, it's I going horizontally and j going vertically down. How do you map that into a sort of linear index? When we do a lot of the CUDA programming, this will come up again as well, because you usually never have to do this manually yourself, but in CUDA you do. So the point I want to make, we're using column major. And the reason we make this distinction is because it makes a big difference in performance. So these two functions on the right show basically just adding two matrices together and storing the result in another matrix or another matrix. And the only difference between them is the row major one goes row by row, and the column major one goes column by column. That is the only difference between these algorithms. Yet on this sort of input size I've chosen, it takes about 27 milliseconds for the row major one to execute, but it takes like 1 millisecond for the column major one. So there's a difference of like around 25 to 30 times difference if you're indexing the array the wrong way. And this also extends if you have sort of n-dimensional matrices like 3, 4, 5, 6. The sort of heuristic I use is the leftmost indice, you want that in the innermost loop, and then progressively outwards. So for the column major, you want this I loop. I is the first index. You want to do that first before you move on to the j loop. Okay. So these are like your sort of multi-dimensional arrays, but all multi-dimensional arrays are just stored in a sort of linear block of memory anyway. So Julia lets you just linearly access the elements as well. So even like these are the same arrays. I think they're 1024 by 1024. You can just simplify it into one for loop instead and just sort of go over the indices linearly. So if you have like a 2 by 2 matrix, you can index it by the elements like 1, 2, 3, and 4. And the way it will look in memory is you'll go down sort of column-wise, like shown in the diagram as well. And this is doing this sort of linear indexing is basically the same speed as doing your column major indexing. Okay. Yeah, I'll finish this part off and then call it that. So one thing that I've been alluding to a lot is talking about allocations and allocating memory. And when we say allocations, technically we could be storing things on the stack or on the heap. But we usually, when we say allocations, we mean heap allocations. And if you're saying stack allocations specifically, we'll use the word stack. Allocating memory here can be quite costly because you have to find a bit of space that's big enough to store your object. So we saw arrays are stored contiguously in memory, which means you have to find a block large enough to store the entire array there. You can't find two small blocks that add up to the same memory space. It needs to be contiguous, like next to each other. Also, when you stop using the memory, it has to be cleaned up by the garbage collector. And for this garbage collector to run, it has to interrupt your processing. And so it will actually stop calculating your results while it cleans up the memory for you. So this can be a huge impact on performance. Just to give an idea, so again, this is a technique that people may be familiar with if you've used NumPy or Python. When you're sort of calculating results, it's best to sort of pre-allocate where your results are going so that you're not, you want to pre-allocate your results so you're not needlessly allocating memory when you're resizing an array. So what happens when you're appending to an array? If you have an array that's one element to begin with, you have enough space in memory for that one element. Now, if you need two elements, you might not have enough space to grow, so the entire array might have to get copied to a different block of memory with enough space for the two elements. And this keeps getting worse and worse the more you append to it. So these algorithms are basically exactly the same. The only difference is one pre-allocates the size and the other one just appends to the array. And this is a log-log scale, which means this red line is like orders of magnitude worse for every n input you have. So yeah, if you're writing performance critical code, always try and pre-allocate. Don't change the size of your arrays because it has terrible, terrible performance. This tip is the same regardless of what language you're using. Just appending to arrays is not a good idea. So one way to get around this is you can sort of reuse some memory that you have allocated because you will probably need this memory at some point. So this first function basically has to allocate an array for like the numerator variable, the denominator, and the final result as well. So it's allocated 3 times within there. But all of these arrays are exactly the same size, so you can rewrite the function and pass in this Y array and reuse that memory throughout. And again, you'll see this broadcast notation, this dot equals, will basically say put the results in the array that's on the left-hand side instead of allocating a new array. So it will overwrite the memory in there. And very common in Julia, you'll see this exclamation mark on the end of function names, which you will have seen a lot. This is just notation. It has no effect on how the function actually works, but usually you put this exclamation mark on the end to indicate that the first argument will get mutated or changed by this function because it's using the memory there. It's called the sort of bang notation. So main reason you do this is you're not allocating memory needlessly, and it makes a big difference, or it can make a very big difference on speed. And if this function is used within an inner loop, instead of having to allocate memory every time you call the function, you can just allocate it once at the start, reuse it for the 1,000 times it's in the loop, and then let it be garbage collected at the end. So yeah, usually you're just moving your garbage collection and your allocation outside of like the hot loop of your program. So the hot loop is where the program spends the most time. If you've just got sort of one function that takes a long time and allocates once, then you're not going to get much speed improvement by sort of moving the allocation somewhere else. One big thing that will help for your assignment is whenever you slice an array, so you should be used to this in Python or NumPy, you can take a small section of an array and get a new smaller array from it. It's called slicing. If you do that in Julia, it will create a copy of your array. So every time you do a slice, it will create a copy. And you have to explicitly use what's called a view to instead do what you think it should do, is just be like a little window into where that memory already exists. So there are some issues with views, like if you change the values of a variable that's a view into another array, your other array will change those values as well. Also if you're, for example, let's say you're creating a view into this array that selects the first row. These are no longer contiguous in memory. So the performance operating on a row slice or a row view might actually be far worse than if you're operating on just a column, like arrays next to each other. So you have to keep that in mind as well. Sometimes it might be better to just make a copy. Yeah, so final one. You can avoid the heap altogether if you know what size of your arrays are. So there's a package called static arrays, which lets you create usually pretty small arrays, like sort of less than 100 elements. If you know the size at compile time, you can actually allocate these on the stack instead of the heap. This is basically the same as if instead of, like usually you'd write your sort of position vector, let's say, of like a particle as an array with 3 elements. One way you could move to the stack is by having 3 variables, x, y, and z, which are just numbers, which obviously makes your code much harder to read. This basically does the same thing, but gives you some nicer syntax to still work with arrays, but make sure they're allocated on the stack. So I'd recommend looking into this for doing the assignment as well. Main thing is they're immutable as well. So once you create one of these arrays, you can't change the elements within it. You have to create a new array, which is not as bad as it seems because it's on the stack anyway. I'm going to skip this and do it next time as well. But this is a way that we can use to actually find where bits of our code are allocating, so we can sort of work on it and remove it. Okay, I'll put the link to the assignment on the website tonight, so you can all sign up there. It's on the resources page. But the assignment will just be optimizing a very bad implementation of the nearest neighbor algorithm. So writing your own version that's a lot faster. And all of the task details are in the README. Okay. I'll just check Teams for any questions. Does anyone have any questions here? Teams? Okay, great. All right, I'll see everyone on Thursday.